Hey everyone, in this video we're looking at random variables. A random variable is a quantitative variable, so it has numerical values, whose value is determined by some kind of random event. We often write these with a capital letter like X, Y, or Z. Some possible examples would be the number of heads when you flip 10 coins. So if you flip 10 coins, you'll get some number of heads between 0 and 10, but we don't actually know what that would be because it's random for each coin flip. Next example is the number of baskets when I make 10 free throws. So that again could be anywhere from 0 to 10, but the probability of any one of those outcomes is potentially different, and the result would be one of those 0 to 10 numbers, but we don't know what it would be at any given time. And the third example I have is the weight of a newborn baby that's randomly selected within the US. This third example is a little bit different than the other two because both X and Y, the first two random variables here, are discrete random variables. And then the last one is a continuous random variable. Because the weight of a baby is not whole numbers, it's not specific values, but it could be any number on a number line between, whatever a reasonable range would be depending upon your units, maybe between 2 and 15 pounds or something like that. So there aren't fixed possible outcomes for that last random variable. And when we talk about probability distributions for these different random variables, continuous random variables work quite a bit differently than discrete random variables. So in this section, we're focused on discrete random variables. And then in the next chapter, we'll see continuous examples. The probability distribution of a discrete random variable is usually written as a table or sometimes as a formula. So here's an example. My example random variable here is the number of men in a sample of size 5 that are colorblind. So if I look at a group of 5 men, they could all be colorblind. There might be 5 colorblind men. There may be 2 out of the 5 is colorblind. Maybe none are. So the possible values of X are everywhere between 0 and 5, but this does have to be a whole number because it's a count. So for our discrete random variables, we typically can write out all the possibilities in a table and then list the probability of each of those outcomes. These probabilities here are computed based on the fact that 8% of men in the general population are colorblind. Sometimes these probabilities might be generated with some sort of theoretical probability formula. Sometimes they might be collected based on empirical evidence. So the probabilities I'm seeing in this table, the probability of X equals 0 is 0.659. That means that's like a 65.9% chance that 0 of the 5 men in the sample would be colorblind. For any probability distribution for a random variable, we do need each of these P of X or probability values to be a number between 0 and 1, including 0 and 1. Otherwise, they're just not valid probabilities. And also important is that the sum of all of these P of X values needs to be 1. It can't add to more than 1 because that would represent that some of these X values could happen at the same time, and we can't have X be 1 and also 2. And it can't be less than 1 because that would imply that there are X values that aren't being accounted for in that distribution. So 100% of the possible values have to be listed in the table and then have a particular value. You'll notice in this table, the last option, 5, is written as 0 plus. The probability of getting 5 men that are colorblind is not actually 0. That is possible, but it's smaller than the rounding in this table. So the decimal is less than 0.001. It rounds to lower than that. So that's what that 0 plus means. That also means that if you add up rounded values like this in a table, it might not be exactly 1, but as long as it's 1, 2, in this case 3 decimal places or whatever is relevant to the probability rounding, that's okay too. So here's a sample question we might ask. What is the probability of seeing 2 colorblind men in a group of 5? This is something that I just read directly from the table. So this would mean x is 2. I look in the row with x value 2, and the probability value listed for that is 0.050. So the probability of seeing 2 colorblind men in a group of 5 is about 5% or 0.05. Another example, what's the probability of seeing 2 or more colorblind men in a group of 5? So this would involve multiple options in this table. So we'd be looking at the probability that x is 2 or 3 or 4 or 5. So I'm going to take all of those probabilities and add them up. I am using the addition rule here, but because these are all mutually exclusive events, I can't have x be, 1 and also 2. I don't have to worry about any kind of overlap. I would just add those numbers directly. So 0.05 plus 0.004 plus 0.001, this ends up being 0.055, or we could think of this as 5.5%. We often see probability distributions written as tables, but I could also graph this information on a bar graph. So here I have the x values, the random variable along the horizontal axis, listed 0, 1, 2, 3, 4, and 5. And then for each of those values, I have a bar where the height of the bar represents the probability. So these probability numbers go from basically 0 at x equals 5 and all the way up to about 0.65, which is roughly the probability of 0. So we can get a nice visual distribution of the probabilities of this random variable, and think about this in terms of a relative frequency. So if you were to sample a group of 5 men over and over and over and over and over and over, we would get a histogram, a frequency table that looked basically like this. Most groups are going to have no colorblind men. About 30% of them would have 1. About, 5% would have 2. And then we'd see very few with 3, 4, or 5. I didn't include any representations of probability distributions as functions here, but you will see this when we get to binomial variables. Just to wrap up, I wanted to mention what exactly we're going to do with random variables and these probability distributions. One would be to answer questions that I looked at in this video, meaning to find probabilities of specific outcomes. So we're just using the probabilities from the table or from the formula or however they're determined to find those particular outcomes, how likely they are. Another would be to calculate the mean or the expected value. So this is sort of the long run average. If we were going to do this random experiment over and over and over again, what would we expect on average to see from X? And this is an important question to answer about our random variables. Going along with that, because of that randomness, our x values are going to vary from the expected value or the mean. So we can also look at the standard deviation or the variance of the random variable. How far away from the mean does it get in typically? And finally, we're going to be interested in determining which outcomes of the random variable are sort of typical versus which are more statistically unlikely or extreme. And this thought process of identifying extremes is really important when we get into statistical inference. That's it for this video. Thank you for watching.